Today we will discuss few problems based on the intensity of the coherent sources. Let's see. The first problem says the intensity of two coherent sources is in the ratio 9:4. That means intensity of first to the intensity of second is given as 9:4. What is the ratio of the maximum intensity and the minimum intensity in interference pattern? If we have an interference pattern, there will be certain points where intensity will be maximum, and there are few points where the intensity will be minimum. So we want to find the maximum intensity divided by the minimum intensity. Let's see. What is the data given to us? I1 upon I2 is 9/4, and we want to find what? Imax upon I minimum. Let's see how to find. For maximum intensity to minimum intensity, this ratio, we need something called A max and A minimum, because we know I in intensity is directly proportional to the square of amplitude. So we need I max upon I minimum. So we will have to find A max upon A minimum. But before that, let's see what is given to us. I1 upon I2 is given to us. We know I is proportional to A square, so we can write I1 upon I2 is equal to A1 upon I2 square. Now I1 upon I2 is given as 9/4. We will get A1 upon A2 is equal to 3 upon 2. Now we know I max upon I minimum will be A max upon A minimum square, similar to this. Now A max, we know maximum amplitude is A1 plus A2, and minimum is what? A1 minus A2. So we substitute the values. We know that A1 and A2 has some relation. So we will substitute A1 is equal to 3/2 times the A2. When we substitute the value, A2 will get cancelled from numerator and denominator. We will get 3/2 plus 1 and 3/2 minus 1. So after solving that, we will get 5/2 and 1/2. And we have to take the square. So this 2 and 2 will get cancelled. You will get 5 upon 1 square, which is 25/1. So this is the ratio of the maximum to the minimum intensity if the I1 upon I2, which means the intensity of the coherent sources, is 9:4. Now let's consider another problem. Question says, if the widths of the two slits are in the ratio 4:1, that means that slits are in the ratio, having the widths in the ratio 4:1, then what is the ratio of the amplitude of the two interfering waves? That means we want the ratio of the amplitudes for the waves for the first divided by the second. Let's see how to find it. Given is what? W1 upon W2 is equal to 4:1. Width ratio is 4:1. We want to find A1 upon A2. How to find it? We know more the width, more the light, more the intensity. That means width and intensity are directly proportional. So if we write W1 upon W2, that will be equal to what? I1 upon I2. But W upon W2 is given as what? 4:1. So substitute this value. So we will get I1 upon I2 is equal to 4:1. Now again, we know intensity is directly proportional to the square of amplitude. So we will write I1 upon I2 is equal to A1 upon A2 whole square. We already know I1 upon I2, right? Take this square to this side, you will get square root. A1 upon A2 will be square root of 4:1, because we already know I1 upon I2 as 4:1. So we will get A1 upon A2 is equal to 2:1. I hope you have understood both the problems. In both the problems, we studied or we understood something spatial relation. What is the spatial relation? I proportional to A square. Hello students. Let's consider few more problems based on the intensity of the coherent sources. We have a question. Find the ratio of the intensities at points x and y. That means we want intensity at x divided by intensity at point y. When the two interfering waves have a path difference of 0 and λ/4. What does that mean? That at point x, we are going to have a path difference of 0, and at point y, we are going to have a path difference of λ/4. So let's find out. The data given to us is very simple. The path difference in the first condition, delta x1 is 0, and delta x2 is λ/4. Nothing else is given. And we need intensity at x divided by intensity at y. How to find it? Now to find the intensity, we must know the resultant amplitude at that point, because we know I is proportional to A square. And to find the resultant amplitude, we must know the phase difference between the two interfering waves. And to know the phase difference, we must know the path difference. Quite confusing, right? So let's start solving. For point x, we can write step number A, the phase difference at point x is equal to 2 pi delta x1 upon lambda, and delta x1 is given as 0, so phi at point x will be 0. Now we know that resultant amplitude at point x would be square root of a1 square plus a2 square plus 2a1 a2 cos phi, where phi is the phase difference at point x. Since this phi is 0, cos 0 is going to be 1, so we will get square root of a1 square plus a2 square plus 2a1 a2. This is nothing but square of a plus a2, right? So square and square root gets cancelled. We will get a1 plus a2 is equal to amplitude at point x. Now we know in interference pattern, we will get a1 and a2 equal. Why? We have already understood the conditions in the interference pattern. For steady interference pattern, a1 and a2 must be equal, right? So if a1 and a2 are equal, so ax will become a plus a, that is 2a. Now let's go for point y. For point y, what can we write? Let's see. We can write phase difference at point y is equal to 2 pi delta x2, that is path difference at point y, divided by lambda. Now this value is given as lambda by 4, so 2 pi into lambda by 4 divided by lambda. So this 2 and this 4 will be cancelled to give us this value. This lambda and lambda will be cancelled, so we will be left with phi, that is phase difference at point y, is equal to pi by 2. Now let's say step number B, the resultant amplitude at point y would be square root of again a1 square plus a2 square plus 2a1 a2 cos of phi at point y. Now phi has come as what? Pi by 2. We know cos pi by 2 is what? 0. So this term will be 0. So we will only get a1 square plus a2 square. Now again, if we say a1 is equal to a2, we will come to know that this ay is going to be square root of a square plus a square, which is simply what? Square root of 2a square. So we will get ay is equal to square root of 2 multiplied by a. Let's call it as equation number 2, and let's call it as number 1. Now we know I is proportional to a square, therefore ix upon iy would be a at x upon a at y, the whole square. And we know the values. Ix upon iy would be is equal to, ax is what? Twice the amplitude. What is ay? Square root times a, and we have to do the square. A and a will be cancelled. You will get 2 upon root 2. If you square, you will get 4 upon 2. What is 4 upon 2? 4 upon 2 is 2 raised to 1. We will get the ratio as 2 raised to 1. So this is the ratio of intensity at point x and y. Let's look at the numerical based on diffraction. Question is, a screen is placed 50 centimeter from a single slit which is illuminated with 6000 Armstrong light. We can write two data. Number one, that the distance of screen from the slit is 50 centimeter. So we can write 50 into 10 raised to power minus 2 meter. You know the conversion, right? Next is wavelength is given out to be 6000 Armstrong. 6000 Armstrong can also be written as 6000 6 into 10 raised to power 3 into Armstrong can be converted into meter by multiplying 10 raised to power minus 10. So in 10 raised to power minus 7 is to come. Wavelength is given to us. What else is given to us is the distance between first and third minima is 3 mm. That is y3 minus y1 is equal to 3 mm. We can write 3 into 10 raised to power minus 3 meter. And what is asked to us? What is the width of the slit? We need slit width A. How can we find? Let's draw a simple diagram. Let's say if we draw a diagram here. This is our screen, let's say. And we have a slit here, somewhere around here. Very narrow slit. From here, if you look at this distance, this is your capital D. Here you are going to have central maxima, and somewhere around here you will have your first minima, and somewhere around here you will have your third minima, right? We know third minima is going to be at a distance of y3, right? From central maxima to third minima, the distance is y3. That means this much of height is y3, and out of which this distance between central maxima and first minima is going to be y1. So if we want the distance between third and first, we have to write y3 minus y1, and that's given to us 3 into 10 raised to power minus 3 meter. Now we need to find the value of A. How to find it? Let's draw these two lines. What can we see? Here the angle is going to be, let's say, theta 1. Here the angle is going to be, let's say, theta 3. Now we know one formula. What is that? That A sine theta is going to be equal to n lambda if it is a minimum intensity point in diffraction pattern, right? So let's write for first minima. What can we write? That A sine theta 1 equal to 1 into lambda. Now theta 1 can be approximated to theta or tan theta, you can say, since theta is going to be very, very small. So if we write sine theta 1 as tan theta 1, we are absolutely right, because theta is very, very small and measured in radians. What is going to be tan theta? This height upon this base. What is this height? This is y1 upon the base is going to be capital D equal to lambda. So from here we will get y1 equal to lambda D upon A, right? Similarly, we can write for third minima also. For third minima we can write y3 equal to, we have multiplied lambda with 1, right? Because it was first minima. For third it will be 3 lambda D upon A. In a similar manner we can write. Now Let's subtract these two. So y3 minus y1 will give us 3 lambda by a multiplied by d minus lambda by a multiplied by d. Something is going to be common. Lambda d upon a will come out as a common term. We have 3 here, and if nothing is written here, we write it as 1. So 3 minus 1 will give us 2. And this value is already known to us, 3 into 10 raised to power minus 3. Now only unknown to us is a. So let's put the value of lambda in d. Just rearrange the terms. So 2 into 6 into 10 raised to power minus 7, which is given in our data, into d is given as 15 to 10 raised to power minus 2, because it's in centimeter, we have to convert in meters. And you have to write 3 into 10 raised to power minus 3 in the denominator. So let's simplify this. So you will get a is equal to, so let's simplify this, 3, and this is 2 times, 2 into 50 will give you 100, into 10 raised to power minus 2 will get cancelled. We will be left with 2 into 10 raised to power minus 7 upon 10 raised to power minus 3. So finally we will write 2 into 10 raised to power minus 4 meter, or you can also write it as 0.2 millimeters. I hope you have understood this numerical. Thank you.